Alright, so now we're going to talk about what happens when the electric and magnetic fields interact. And what you end up with is electromagnetic waves. James Clerk Maxwell, was looking at all the symmetry between electric and magnetic fields and came up with this set of equations, tied them all together. So he used both of Gauss's laws, Faraday's law, and then he made an adjustment to Ampere's law in order to describe electromagnetic waves and their interactions. So now mathematically we have the idea that electromagnetic waves can exist, and so the next piece is to experimentally show that, and Hertz's experiment showed it. He had a circuit hooked up that would cause a spark to be created, and then a space between that and something that would receive a wave, if a wave would travel. And certainly the wave did travel, and it did induce a current in the wire, and a spark occurred in the wire. Now the spark didn't fly from what you see in the picture here, loop 1, to the receiver. Nothing was there. You had a spark, and then you got another spark with nothing visible in between, showing that there were electromagnetic waves. So one of the next big pieces to it is the idea that electromagnetic waves all move at the speed of light, which is 3 times 10 to the 8th meters per second. This is the speed of light in a vacuum. Speed of light in air is not much different. It's not worth worrying about. Here are some of the equations that you might find useful. So electromagnetic waves move through a vacuum. They all travel at the speed of light. And for our purposes, they're in all directions. So this all comes together in what we call the electromagnetic spectrum. This graphic right here has all the wavelengths. The biggest of the wavelengths are radio waves, and they get smaller and smaller until they get to the gamma rays. We've divided them into ranges by wavelength. Some of it is by how they're created, some of it is by their effects, but they do neatly divide up. And some of the things to know are the larger the wavelength, the smaller the frequency. They're inversely proportional. Think back to your wave equations. And also, the larger the wavelength, the smaller the energy. So energy and frequency are proportional. So the ones with the higher frequency are going to have the greatest energy and do the most damage. So should make sense. You've got the gamma rays there that are very high frequency, and they do cause a lot of damage. So if we start off with the biggest wavelength and lowest frequency, we start off with the radio waves. One of the things that you're familiar with probably are AM and FM radio. AM changes the amplitude of the wave to carry the sound, and FM actually shifts the frequency to plus or minus 100 hertz, plus or minus 100 kilohertz from the value of the radio station in order to carry the signal to your radio. So we have microwaves, and those are caused by the thermal motion of atoms, and they're used for satellite transmissions, Wi-Fi, Bluetooth, and cell phones. Infrared is basically heat caused by thermal motion. Visible light is what we see. That's the colors of the rainbow, the Roy G. Biv. Basically 400 nanometers to 750 nanometers of wavelength. It's made up when atoms vibrate and electrons transition from one energy level to another inside the atom. Ultraviolet is created by atomic motion and electron transitions again. And X-rays, once again, same idea, but besides the electron transitions, you also get electron collisions. A little bit higher energy. Gamma rays, they're a type of radiation. They are an electromagnetic wave emitted by nuclear decay.